Now that we got familiar with the LSTM module structure, let's take a step back and look at a special kind of sequence, time series data, in more detail. In this section, we will review the structure of time series datasets and prepare to apply LSTM networks to time series. There are time series problems all around us, all kinds of things and phenomena that are measured over time, and there are clear trends, simple or complex, how these measures increase, decrease, seasonally change, fluctuate, or grow or shrink in variance over time. Also, predicting anything in the future, the ultimate domain of time series, is the goal of most prediction models. On this slide, there are just a few examples of time series problems. In a retail situation, it is essential to forecast how many items will be sold this week, this month, this year. We might also try and predict earthquakes, where of course the time component is crucial. While we understand that over time more and more tension builds up in a fault line, it remains exceptionally difficult to correctly predict when exactly an earthquake will occur. Finally, fraud detection models can also be seen as a time series problem, when a certain user account can show a sudden change from its usual behavior, or that a set of transactions, one by one, do not seem suspicious, but in a sequence they clearly show inappropriate activity. Now, if we wanted to use a classic supervised machine learning model, specifically a regression model, to solve a time series problem, it can be non-trivial how to exactly define our features as well as our target label. Of course, our target label is future values, but in 1 second, 1 day, 1 month, and for how long of a period are we predicting? And going back to features, and we need features because the raw past values might not work very well to capture the series, we might have to define a whole range of statistics over different past time horizons, and there is no one clear way to know how to best define these. So to take an example, let's look at a specific time series. We just as well could have taken an example from a stock market dataset, such as a share price over time, but in this case, let's look at another market, the median price of New York City real estate over time. As you can see, for each week, the median value of house sales is recorded over a course of a few years. Given this time series, then the way to build a supervised learning dataset is to run through the time sequence with a sliding feature window together with a label sequence for each window after a certain horizon. That is, we are collecting our input signal features as statistics from inside the sliding window, and we are using each to predict the label or sequence of labels at a fixed relative distance range from the sliding window in the future. Here is an example for creating features. In this case, our first sliding window plus its label, the first row on the right side, corresponds to the window of the first 3 rows on the left side plus the 4th row as the label, and so on until the last right side row corresponds to the last 3 + 1 rows on the left. As you can see, here we have the simple label of the last single value and the simple statistics of the previous 3 values. It is useful to actually create a function to which we can just pass the original dataset as well as the required window size and horizon and potentially the length of the prediction window to automatically create the restructured table. An example for such a function is shown on the slide and is available in the linked GitHub repository. It is also useful to consider preprocessing dates to provide strong feature signals. Initially, we might think that dates are nothing but just numbers, and we could certainly use them that way too. However, for many practical scenarios, it does make sense to explicitly create day of week, month, year features, as well as holiday flags, and so on. Once we are done with this restructuring, we need to consider data partitioning, that is, how to split our data for training and testing. Unlike other supervised learning problems in general, where often random split is the best, in this case it is very important to make sure that our test set is strictly later than our training set to avoid data leakage. Then we can train based on all the available rows in this earlier, typically larger portion of our time series, and use the later, smaller portion for testing. Finally, we can predict by taking the last available sequence parts as our input and predict into the unknown future. If we need multiple time points in the future to be predicted, this can be accomplished in a number of ways. For example, we could explicitly define the length of our prediction window in our earlier preprocessing function, or we could just recursively apply a forecasting model, forecasting a single value, and bootstrapping one prediction as a new feature for the next. So let's start building actual models. It is always a good idea to start with one or more baseline models, for example, using a long time average or just the last available value as our baseline forecast. Any other, more complex model should be able to provide more accuracy than these baselines to be useful. One approach, as you can see on this slide, is to use the classic powerful supervised learning algorithm, random forest. While random forests are not specifically designed at all for time series or even sequences, they can still prove useful as we transformed our data into a supervised learning structure. However, recall from the earlier lecture that we just explored how sequence models, such as RNNs, can understand more of the structure of sequences. Therefore, in the coming lab, we will actually use an LSTM model to predict time series, and we'll be able to compare it with our baseline as well as our structured random forest model.